Now let's change our gear. Okay, let's go into discussion and recap of the number representation that you all are expected to know by this time from your previous class of CS47 or equivalent about this. But since we need this, we'll just quickly go through the basic concept and so that you kind of you can brush up your memory onto that topic. So what we know and relevant to our study is that there are multiple number system, and arbitrary number system also can be implemented. But point is that there are standards like a decimal number, for example, which we all understand. We can all kind of sense, kind of perceive the decimal number system. But there are more interesting number system like a binary with respect to the computation and electronic computation world. An electronic system, electronic computer understand the binary number system, and everything is implemented based on the binary number system inside a computer. And there a binary number, a string, a big string of binary numbers or values can be compactly represented with octal or hexadecimal. Okay, so difference between these four systems or any other system, they are these that symbols can be similar or different, right? For example, here for this four category, symbols looks like same, right? We are using either 0 to 9 or 0 to 0 and 1 or 0 to 7. And for hexadecimal, we extended our symbol set with adding letter characters or characters from A to F. And by the way, it doesn't matter whether you make it a small or capital letter there, they makes the same value. Value wise, there's the same. Okay, so you can either write a capital A or small a, but when you are writing a hexadecimal format, stick to one convention. If you write everything that letter symbols as capital, stick to that. Okay, don't mix up. Okay, or you can stay to the small. Okay, stay small. Like don't mix up capital and small letter there. All right, so we are using different symbols, and the number of symbol we are using in a number system is called a base. For example, decimal uses like 10 symbols, so it's base 10. Binary uses 2 symbols, it's base 2, and so on and so forth. Now, when we manipulate numbers and do some problems, like especially the format conversion and stuff like that, it is very important to write a subscript of the base of the system. Okay, we need to write the base of the system as a subscript of the value. So for example, like I can write, imagine like I have written 10, right? And I know all these four of the system uses that two symbols, 1 and 0, right? Now, depending on what base we are talking about, its value gets changed. So number are nothing but a representation of value, like literal representation of values. So depending on the base, which base we are talking of, its value changes, right? 10 in the decimal is 10, and we all understand what the 10, the value as a value, what is a 10, we can sense it, right? However, like 10 in base 16, it's not really we cannot really immediately perceive because we are not that used to that number system, right? 10 in base 16 or hexadecimal, in fact that value is 10, right? 15, 16. That value is 16, like from a decimal perspective. And octal, for example, we cannot perceive also like readily what is the real value of this representation in the octal, like 10. Like similarly, binary, it represents value of 2, right? So if I just write 10, since we know there are different number systems and we are dealing with the different number system in a specific problem, we have to make sure we also convert what base we are talking of. Okay, so this is important thing, at least when we are doing problems with the number representation and conversion of the number, please make sure you're writing down the base. All right. Now, little bit refresher on how to translate different representation to the decimal and vice versa, right? Because why we are interested in that? We are interested in that mainly because we understand decimal number system better, right? So given a binary or hexadecimal or octal, how we can convert it into this decimal value so that we can understand, we can perceive its associated quantity, right? Its associated value, and vice versa. Also, like we have a decimal value and we want to convert back to the binary or hexadecimal because computing system uses binary, so we need to be able to convert it into binary. Right? So the formula here to convert a n digit number, okay, means there are n symbols in that number value representation, that is in the base k into now we want to change it to the corresponding decimal value. That value is sigma, sum from 0 to n minus 1, where n is the number of digits. So here what we are doing, we are indexing these symbols from rightmost side as 0 to the leftmost side as n minus 1. So rightmost side index of that series of symbol, rightmost side symbols position is 0 and leftmost side is n minus 1. And then D is the decimal equivalent decimal value of the symbol, right? For example, what I mean by that equivalent decimal value is this. Like in the hexadecimal system, A, B, C, D, E, F has corresponding decimal value for that symbol. A is 10, B is 11, C is 12, D is 13, E is 14, and F is 50. Okay, so that's their symbol's value, corresponding decimal value of the symbol. So we are talking about that corresponding decimal value of the symbol for that number system. At position I, you multiply it with base of that number system to the power I. Okay, and you sum them all from 0 to n minus 1. And with summing them up, you get back your value represented in decimal number. Okay, and then how do I do other way? Like I have a value and I want to convert it into a decimal into a base of k number. Okay, in general, like k can be 2, k can be 16, k can be 8, depending on whether we are talking about like binary, hexadecimal, octal, etc., etc. Okay, or any arbitrary number system which has like k as maybe has 5 or 7 or 21, who knows, right? So in general, let's say programmatically, let's understand. So we set an index to 0, so that means we are determining the numbers, like each symbol, and starting to put them in an array. Okay, like that array, let's call it a array of digit. Now we are converting a number, decimal numbers, into corresponding base k representation. So we are looping through till the number is 0. Okay, till the number is 0, and then at each step we are determining the quantity remainder into num, like modulus operation, integer modular operation of k. Okay, so this is a modulus operation. This will give you the remainder value of the division operation corresponding, and we are just placing that value into the remainder, storing that in a remainder, and then reducing the number value or number with a division or quotient of the division operation. Okay, so we are computing basically remainder with respect to k for that number, and then reducing the value of the number by the quotient to the quotient of the division operation with k, and then we are storing the digit into the index, into a place in that array dictated by the index, which is starting from 0. We are putting them as a remainder, okay, and then we are increasing the index. So we do this process for till we hit a number not 0, okay. We hit that process, and then what happens, remember, like this remainder is still a decimal value, so we need to convert it back to its symbol. Like let's say my remainder, let's say we're talking about base 16, or which is hexadecimal, and my remainder is, let's say, 12, right? So instead of writing 12, I need to write C instead. Okay, so I need to map that remainder value to its corresponding symbol. All right, and then the last but not least trick is this. Remember, we have started from a higher value remainder and going towards and this number is diminishing lower and lower and lower, and that's remainder being pushed from 0, 1, 2, 3, 4, etc. Okay, now when we write down that corresponding digits from this array, we go in a reverse order. Okay, we go from the n-1 location till 0 and write it down from left to right. Okay, in other sense, your 0 your 0 is zeroth index is your least significant digit, whereas the n-1, the last element of the array, is the most significant digit in the whole converted numbers.